All right, hello everyone. My name is Alex Crichton, and as I was so aptly introduced, I work on Rust at Mozilla. I'm going to be doing one of my favorite things tonight, which is talking about Rust. So first things first, Rust is a programming language coming out of Mozilla Research. That's what I'm primarily employed by, and it's kind of the sponsor behind the language. It's not really entirely a Mozilla project. At this point, there's been I think for a long time now, the amount of community contributions have outnumbered the amount of contributions in terms of commits that the actual members of Mozilla has. So this is much larger than Mozilla now, but they were kind of the driving impetus for it early on. So first off, I thought I'd tell you what is Rust. So if you go to rustlang.org and you take a look at our website, the first thing you'll see is Rust is a systems language, or a systems programming language that runs blazingly fast, prevents almost all crashes, and eliminates data races. And then this is kind of like a little sample of the syntax. You can see it's a little C-like, some fun things you can do, and I'll kind of drill down to these points. And I'll send out these slides later. I have these links at the bottom called Playpen, where you can just click on it and you run Rust in your web browser. I might do that a few times here. I also want to say, if anyone has any questions, feel free to raise your hand, shout, throw things at me. It's fine. I don't know. All right. So a lot of times when I tell someone about Rust and I say, hey, it's a new programming language, they say, well, wait, why do we need another one? We have so many of these already. So I like to describe it with this kind of spectrum here. So a lot of people see this spectrum of safety versus control, or safety and control versus, safety versus control. So C++ and C on one end, they have a lot of control over the hardware that you're running on. So you can optimize it really well. You can translate it directly to assembly code. Like, you know exactly what you're writing, how it's going to be translated. But it's not very safe. It's very easy to segfault, very easy to blow your leg off, very easy to have things like heartbleed, various vulnerabilities like that. Now, on the entire other end of the spectrum, we have languages like Python or Ruby or JavaScript, where they have very little control over what's going on. Languages like Haskell, it's actually very difficult to even reason about the runtime of your program. But they're very safe. They can't segfault. You can get some exceptions, but that's pretty contained. You can't. It's very hard to have security vulnerabilities that wouldn't be prevented otherwise. And so in the middle, you have these languages like Java, which you can kind of have some weird segfaults in, but it's generally very highly performant with their JIT and everything going on. But what Rust does is Rust just steps off this line entirely. Rust says, no, we're going to give you all the control you can have, plus all the safety you can have. So this is kind of the driving goal of Rust, is kind of break this whole spectrum paradigm and just kind of step completely off. So the first thing that I said is that it was a systems programming language. And what this really means is you have a lot of really interesting properties like fine-grained control over allocations, or we're not going to require a garbage collector in the way that C++ does it. There's essentially no runtime at this point, and it's very close to the metal. So like C++, you can look at some Rust code and you can reason about exactly what assembly code is going to be generated, and you know exactly how it's going to be run, and you can kind of have very concrete guarantees about the performance of your code. So the next thing that I said was that Rust runs blazingly fast. And I'm serious when I say this, in the sense that Rust is a compiled language which has LLVM as a backend, which taps into all of LLVM's very large number of optimizations. So if you have ever used Clang and you thought that it generated really fast code, we're doing exactly the same thing. And in a lot of places, Rust can actually do better than C++. Rust has a lot of information about aliasing, about how pointers work. I'll talk a little bit about that all later, but Rust can actually, in a lot of cases, get better performance than C++ due to the optimizations that we can enable in LLVM. So one more thing is Rust prevents almost all crashes, is what I said. So this is kind of an interesting thing where Rust is safe by default. Rust is like JavaScript and Ruby and Python, where you cannot segfault. The harder you try, the harder you just cannot do it. So this is a very difficult thing to do when you have this level of control that we give you. But we're able to give you this from a very sophisticated type system with a lot of static analysis, and it can represent a lot of programming paradigms very, very well, and it's very powerful. So we eliminate classes of errors like segfaults, null pointers, dangling pointers, use after free, all that fun stuff you associate with C and C++. It just cannot happen in Rust. So then the last part of that little intro sentence that I said was it eliminates data races. So this is kind of sometimes overlooked whenever I've seen people talking about Rust, but this is, in my opinion, one of the most powerful features of Rust. Where nowadays we have these highly concurrent computers with tons of cores and all these threads running in parallel, but it's really tough to reason about that. It's really tough to write correct parallel code. And what this is guaranteeing is that you cannot write wrong parallel code. You might have some weird kind of interesting stuff going on that is kind of a logic error which you have to deal with, but you can never cite fault, you can never cause an undefined behavior. This is much, much more powerful than a language like C++ gives you. And this is, I'll let it at that. So I'll show how we have these two key concepts in Rust called ownership and borrowing. And by putting these things together, which are very core low-level abstractions, we can build upon that and give you and completely eliminate data races from the entire language. So I thought I'd start out by saying who's using Rust, because believe it or not, there's actually more than a few people using it right now. Primarily, Rust is using Rust. The entire Rust compiler, standard library, the distribution, everything is written in Rust. If you look at our stats on GitHub, you'll see we have some C for some couple bundled libraries and a lot of shell scripts for installation, but most of it's all Rust. And then the other big consumer of Rust today is a project called Servo. So Servo is actually the reason for Rust's inception at Mozilla. It is a project to write a totally parallel layout engine. Where when I say layout engine, you can think of things like Gecko in Firefox, or Blink as in Chrome, or WebKit as in Safari. And what Servo has done is they're building a layout engine, something to render HTML from the ground up. They started at basically nothing. So they're writing it all in Rust. They're going to make it super fast, super parallel, super safe, and it's still very much a work in development. You can see here the picture on the left is the ACID2 test for layout engines. That's now running on a desktop browser, and the one on the right was actually, I think, about a week ago at this point. They've now ported Servo to run on a Firefox OS phone. I'm told the rendering bug is something internally they can fix, but I don't know too much about that. So now I want to dive into kind of some of the key concepts of Rust, and this is kind of the bread and butter of Rust. Everyone using Rust needs to understand a couple concepts that I'm going to explain here, and the one that is most paramount is a concept called ownership. Now, when I say ownership, it probably kind of natively makes sense to you. Kind of think, okay, someone's owning things. I have something, and that's basically what it is in Rust, where there's only ever one person that ever owns a piece of data, and it's a pretty simple concept. But it allows us to express some very interesting patterns. So for example, this is a C program which can go wrong fairly easily. So I have this main function which kind of allocates some memory, stores some information into it, and then I pass it over to a helper function. Now, what's conceptually happening here is this pointer called slot is actually being consumed by the helper function beneath it because it's freeing it. So what this helper function is saying is actually, I'm consuming this and you can no longer use this. But C does not have a way to express that the main function can no longer use slot. So here I go and I use it again and I get a use after free. So I try and free the same thing, and when I run it I get this really weird error that's sometimes kind of difficult to debug. This is a very simplified example, but a lot of times I see this in a much larger scale where it's very difficult to track who's owning things, where pointers are getting freed, and all that fun stuff. So if I translate this, the same code to Rust, it looks a lot like this. So this first line is let slot equals box3. Box is our allocation operator, so what this is creating is a heap allocated integer with a value of 3. And then I pass it to this helper function, and you can see the type of it is box event. It's kind of like generic syntax in C++ if you're familiar with that. And then I just print it out. But the key part of this program is that this doesn't actually compile. On that second call to the helper function, it complains about the use of a moved value. So if we take a look at it over here, we can see that this line right here has, this one right here, you're using the value which was moved up there. And the problem here is conceptually, the first call transferred ownership to the helper function. So the main function no longer has access to the slot. So Rust is able to prevent this use after free at compile time via ownership. So it's not very useful if only I can ever hold onto something. I kind of want to be able to transfer it along. So one part of ownership is you can definitely, once you own something, you can then just decide to pass it to someone else. So if I have a book and I'm done reading it, I can give it to someone else permanently and I don't have to worry about it again. So in this case, we just have a helper function which allocates some memory and then transfers it back to the main function by returning it. So we can see that the main function now owns it after that point and can kind of do whatever it wants with it. And then the other part about ownership is it's a very deep property. So Rust has structures which are kind of, they're basically just a bunch of types that are together with a bunch of named fields. So here I have this A structure which internally has a B structure which internally has that box of an int which is an own value. And I can see that once I pull it out, so I kind of create it, and then the C variable owns that box of 2, I can no longer access it through later. So when I try and compile this program, this last line gets an error because a.b no longer owns, or C owns a.b at this point, so I can't access it. So this is kind of, it propagates deeply within, so I can move entire types at a time or kind of move them out. So it's not a very useful programming language if all I can do is own a value and then transfer that one value all around. Like a lot of times I kind of want to keep this value, or I don't want to have to give it to someone and return it back. So another, out of ownership comes borrowing. So borrowing is a concept in Rust where it's kind of what it implies again. It's kind of, I'm lending you something, but I want you to give it back to me at some point. So borrowing in Rust is dictated with this little ampersand sigil. It's kind of like a, you can see it in C++, but it's a fairly different meaning from it. And here, I have this helper function, which is very similar to the box function we saw earlier, but this program compiles okay, because what the main function is doing is it's loaning a reference into this helper function, which means the helper function is just borrowing it. It's not actually consuming ownership, and then the helper is a little limited in what it can do with it. I'll talk about that in a second. So one of the key parts of borrowing is a borrowed value is only valid for a particular lifetime. So a lifetime is something that we call, which essentially amounts to a region of code or a span of code. You can also think of it as a scope is another good word for lifetime nowadays. So in this case, I declare this variable outside this scope, and I don't actually give it an initializer value. I just say what type it is. And so inside the scope, I declare another local variable, and I try to assign a reference to that to the outside, but that doesn't actually compile. And the reason for that is that the lifetime of this variable is constrained to this scope, but because this is outside that scope, there's no possible way that this can actually reference something inside. So that ends up being a compile time error. So the lifetime is kind of the amount of time which a value is alive for, and you cannot access it outside of that lifetime. That's the whole preventing use after freeze or preventing dangling pointers. So in this case, it's totally fine because because A and B are in the same scope, then the lifetimes end up being connected all just fine. And, I can use A, I can use B, and everyone's happy. So borrowing is an interesting concept where whenever I move something, I'm kind of transferring ownership, and what that's compiled to at the low level is actually kind of copying and moving addresses. So that means if I have a borrowed pointer and then I move the previous thing, then all of a sudden I'm pointing back into stale memory, which could end up being a use after free or dangling pointer. So what borrowing does is it prevents you from moving an object around, which means that while there is an active borrow, I cannot transfer ownership. I still own it, but I can't do anything with it until who I handed it to relinquishes that borrow. So in this case, I declare a vector called A, and then right beneath it, I take a borrow to it. So I'm just going to kind of hold a reference to it. But I can no longer, this is passing it, trying to transfer ownership to someone else, but this is a compile time error because there's an active borrow in scope, and I can still use that after the function, and that would definitely not end well. So this function, which does compile okay, the scope which this reference is contained to is constrained. So once we exit that scope, we no longer have an active borrow, so we can continue to transfer ownership as we used to. So that's kind of where borrowing is moving. Borrowing interacts with moving in a sense to help you prevent another class of errors at compile time. So a common mistake in C a lot of times, which is kind of one of the canonical error bugs, is you declare something on your stack and then you return a reference to it. A lot of static analysis tools can kind of figure this out today, but this is pretty common and kind of a very easy to make mistake when you're kind of starting off in C. So when you run this in Rust, this is kind of the Rust equivalent of trying to return a stack allocated value, you get this big error saying, oh, this function's return type contains a borrowed value, there's no value to be borrowed from. And all this is really saying is that there's no way that I can return a valid reference when it's constrained to just my stack itself. So we can see from here that borrowing allows us to kind of connect lifetimes in a sense, and we can say that this function signature, there's just nothing I can do. I can't actually return that value there, preventing you from using stack frames which have gone away and all that fun stuff. So borrows can also be nested, which is where I can kind of take a borrow and produce a new borrow. So in this case, I have this structure with an inner value, and then this function, what it's doing is it's taking a borrowed structure, and then it's returning a borrowed pointer into the inner value itself. So all this is really getting compiled down to is a bunch of pointer arithmetic, But what the compiler is doing is the compiler is actually having tons of inference here. So it's saying, okay, this pointer is valid for a particular lifetime, so I know that this pointer must also be valid for the same lifetime, and it kind of transfers that borrow. This has some more complicated syntax, but we've actually had a lot of improvements where it gets a lot less noisy nowadays, and it's very clear how that integer came into existence from the origin structure. And so here, I can create on the stack, and then I can call that function to get an inner value to it, and it's all borrowed. I'm not actually moving anything, nothing's moving around. It's all very easy to compile to and very efficient at runtime. So a lot of times, you don't necessarily want to work with borrowed values all over the place. You'll end up kind of hitting some errors in the borrow checker of the compiler where it says some lifetimes are mismatching, or you can't extend the lifetime long enough, or you can't match lifetimes. So in this case, a lot of times you want to go from a borrowed reference to an owned value. So in this case, once I have an owned value, I can kind of transfer ownership, I can pass it around, I can kind of do whatever I want with it. So this is kind of Rust's concept of cloning. I'll talk a little bit about how that's actually realized later on, but what this is saying is just from a borrowed value, I can actually perform some form of operation and then create an owned value out of it, which is probably the same, and then pass it around. So given those two kind of core concepts of ownership and borrowing, I want to explain a little bit how it plays into what we can build on top of it, and one of that is the memory management system of Rust. So Rust has a very fine-grained control over memory management. You can say precisely when it's allocated, precisely when it's deallocated, and you have a lot of control over that, kind of like in C++. But the difference with Rust is that once you create memory, you never have to actually free it. You can decide when to free it, but you never need to call that. It kind of all automatically takes care of itself after the fact. So as an example of this, I was showing you earlier this box operator is kind of a heap allocated integer, which we're going to have to free at some point. So each variable, everything has an owner. So I know that this slot is the owner of that heap allocated integer, and then all I have to do is say when that falls out of scope, because there's only one owner, I can free the data. So in this case, once the function returns, the word slot goes out of scope, it's still the owner of its data, so we can just deallocate it at that point. So this is where, because Rust understands that there is one owner of any piece of data at any time, and it always knows where that owner is, then whenever it goes out of scope, you can just free it. And this is kind of a powerful paradigm which comes out of ownership. C++ kind of has this in RAI sometimes where things can go out of scope and you can run destructors, and Rust is kind of just generalizing that to make an entire memory management system out of it, which I mean, C++ 11 now has nowadays, but yes. So I've been talking about a lot of unique ownership types where with this box operator, no one else can actually hold this box. I can pass out references to the box, but no one else can have a box. So that's not always exactly what you want. So Rust does also have shared memory, where I can have a piece of reference count of data, but we can use ownership to kind of keep track of this reference count. So each reference count, or like this data right here is just a pointer, and all it is the pointer to some data which has a reference count on it. So when I first create it, it's got a reference count of 1. And then I can call this .clone method I was showing you earlier to create a new reference. So it turns out that data2 and data are actually pointing to the same object. They're the same pointer at that point, but they're two independently owned values. So Rust can track them independently, and that means that when I call this function to work with some data, the second copy, then this function is consuming ownership of that pointer, and when it falls out of scope, it knows to decrement the reference count, because it knows that there's no way that anyone else can be accessing this specific pointer anymore, so all I have to do is decrement the reference count and then move on. So at that point, the reference count goes back to 1 from after cloning it, and then I can work with some more data again, and when that one goes out of scope, it hits 0, and once I hit 0, I know that no one else can be accessing it, so I can free the memory. So this is kind of an example of, with ownership, you can not only build unique ownership in the sense that boxes only ever have one owner, only one person having them, but you can also have shared memory where lots of different pointers are all kept track of at the same time. It turns out that reference count of data actually ends up allowing you to build a lot more interesting data structures sometimes. Yes?
If you declared data as a box value instead of an RC, when you cloned it, would it have made a deep copy instead of another pointer?
Yes. The clone implementation for that would actually make a new heap allocated integer. So in this case, data and data2 are actually pointing to the same data, but if it were a box, they would point to completely independent sets of data. Now, an RC pointer has some limitations of it, which a box pointer does not have, but I can go into those later. All right, so a very interesting part about Rust is kind of dealing with the mutability of types and kind of where things can get mutated. So it's kind of, it falls out largely of the ownership and borrowing semantics, but what I should say is, by default, all values are immutable in Rust, and you have to explicitly say that you want to mutate something. So in this case, this is kind of a simple example. Like in the first one, I didn't say that my local variable a was mutable, so I can't reassign to it. But in the second one, I did say it was mutable, so I can reassign to it. And then mutability is also a type of the borrowed pointer itself. So I was showing you earlier a bunch of ampersand references. These are shared references. So that means there can be many, many, many references out at any one point in time. But this one below is a mutable reference, meaning I can mutate it. I can not only read from it, but I can also store right back to it. So borrowed pointers also can freely coerce to one another in the sense that a mutable pointer can actually become a read-only pointer. Kind of makes sense, but you can't actually take a mutable or a read-only pointer and then make it into a mutable pointer. There's some interesting semantics around mutable pointers, and I'll talk about those in just a second. So an interesting part about mutability is that values can actually be frozen. So I have this mutable vector up here, but in this scope, I take a borrow to it, a shared borrow. And while Rust knows that while there are shared borrows, you cannot have any mutable borrows. So this push function is mutating the vector, and because there is an active borrow in scope, I cannot actually take another one and then mutate the vector. So this is actually encapsulating a concept where this could actually borrow the interior of the data structure, and then if I mutated it, I might have a stale pointer. This is typically called iterator invalidation in C++ and Java and a bunch of other languages, or sometimes you get exceptions, sometimes you get seg faults, but this is a part of Rust where with the borrowing system, we can track this and make sure that you never mutate it while someone's holding a read-only reference to it. So once I come out of that scope, though, I can continue to modify the vector because borrows are all lexically scoped currently. So, like ownership, mutability is a deep property of a type. It's kind of inherited through. So this means that if I have this big composite data structure of an A, of a B, of a C, then because the local binding is mutable, it's inherited all the way down. I can modify C, I can modify B, and I can also modify A, and I can kind of do whatever I want with it. And then once I put it into a frozen slot, so this local variable is not mutable. And you notice that this is actually transferring ownership from this local variable to this local variable. It's kind of the concept of moving things around. This word frozen is not actually mutable, so when I try and mutate it, I'm going to get an error, and this is not going to work out. But if the root binding itself is mutable, you can kind of do whatever you want internally with it. So I've shown you how using ownership and borrowing, we can build up memory management. We can build up some abstractions around mutability, which prevent things like iterator invalidation, and give you a lot of guarantees about the pointers themselves and whether they're still valid at any point in time. And now I want to get into something that I find very interesting, which is how we can use ownership and borrowing to build up concurrency abstractions. So this is where Rust is going to fulfill its promise of preventing you from ever having a data race. So as a bit of a background, concurrency in Rust is achieved at the granularity of OS thread. And in the past, we've had we've played with some green threading systems with end-to-end threading based on libUV, kind of like Go. But we have since gone towards a less overhead, or not less overhead, but a less runtime by default semantics in the sense that whenever you spawn something, you can have a separate OS thread and you can run code in and out of it. So one of the canonical ways to have a data race or have some bad memories, you mutate the same object from two different threads. So in this case, I'm going to create a vector, and then in one thread I'm going to push the word foo onto it, and in the main thread I'm going to push the word bar onto it. So this is not valid code. This should not compile because this is clearly a data race. The vector is probably going to get corrupted. So the way that Rust deals with this is that this proc here is a form of closure in Rust, where a proc owns its environment. So in this case, this vector, once I referenced it inside this procedure, it actually moved inside of there. And then because we have moved inside of it, now we can no longer access it outside the scope. So this is actually a compile time error saying that I'm using a moved value. So this is where it's totally fine for any one thread to modify this vector, but only one can modify it at a time. So this is where I'm transferring ownership from the main thread to the child thread, and now it can modify it, but it will have to explicitly pass it back to me if I want to continue on modifying it. So this is where ownership is preventing a lot of, ownership by default prevents a lot of data races, because there is no shared memory by default. You essentially have to opt into it, and I think that's, it's not, but I'll talk a little about shared memory in a second. So I was talking about sending data back to the main thread. So this is where channels are a very interesting concurrency primitive, where in Rust, you actually create two halves of a channel. You have a sending end and a receiving end. So this child captures the sending end by value, so it kind of consumes ownership of it, and then we'll go run some code and send a message back to the main thread, and then this one will kind of do some work and then receive it. So it's this is a bit of an interesting, whenever I see this, I always forget that when you think of a channel, you typically don't think of two halves. You kind of just want this one thing you pass around and kind of send on. But in Rust, if we were to return only one value there, then what would happen is if you sent a message inside this procedure, you just moved it inside there, so you would no longer have access to it outside of the procedure. So this is where, because of the ownership system and kind of move semantics, we actually have to give you two halves to a channel. So one half you explicitly start sending on, the other half you can explicitly receive on, and that can be independently owned by separate threads. So I was talking a little, just to go about shared memory. So Rust does have shared memory across threads, and I'll run this in here, so bigger font as well. So this actually compiles and runs just fine, and what this is actually doing is it's preparing a little bit of a hash map, just kind of have some basic what the colors are. And then this arc is an interesting thing, where that's very similar to that RC that I showed you earlier, and the A here stands for atomic. So RC was a reference counted pointer, it did not have any atomics on it, it was just plain old increments and decrements. But an arc is an atomically reference counted pointer, which means that all increments and decrements are atomic, which means that this type is actually safe to share among all threads. I can safely have this among tons of people. They can all be frobbing the ref count as much as they want, and it's all going to be totally fine. So in this case, again, like previously, I clone it, and that gives me these two pointers point to the same data, but it means that the reference count of this pointer is 2. And then I can independently move each of them into different threads, and then I can print out what's inside the hash map from there. So one thing I find somewhat fascinating about this is that hash map was not written with thread safety in mind. HashMap has no code saying I should lock this, I should make sure that this is synchronized. It's just a plain old data structure, kind of like what you would write in Java or Ruby or C++. You just kind of write your data structure, and by default, Rust will actually make this totally safe. Because Rust knows that when you're accessing a hash map, you're just taking a shared reference, and a shared reference can be shared among many people. You can only read from it, which means that this is actually totally safe. Even though the hash map has no idea about how many threads are accessing it, it's written in a sense that with a shared pointer, it can only have read-only access, in which case you can't have data races. So in this case, the arc is the key primitive here, where an arc knows that it cannot lend mutable pointers. You can only get a shared reference from an arc. And that's because arcs are shared among many threads, and you can't actually mutate it when you have many pointers to it across threads. So this is kind of just an example of where Rust does have shared memory, you just have to explicitly opt into it. And the mechanism of opting in is restricted. So I couldn't store a reference to this hash map inside of the arc. Because what could happen is, if this arc were then a pointer to the stack, then all of a sudden I spawn these threads, and then the main thread returns, and then the threads run, and they're going to have a stale stack at that point. So there are some restrictions about what you can put inside of an arc. But once you get it in there, it's totally safe to kind of move it all around. So that was kind of a high level of some interesting things you can get out of Rust with ownership and borrowing, and there's a whole litany of abstractions that you can build from the ground up with all that. So I want to kind of just give you a high level kind of whirlwind view of some other aspects of Rust. These are just kind of assorted language features, which are kind of nice to have. So like in C and C++ and many other languages, we have aggregate types where you can have name fields, you can kind of put it all together. We have tuples, which means that you can kind of pack things up in any sort of arity of tuple, kind of any length you want. You can assign it to a local variable, you can destructure it in a pattern, so you can peel it all back out. We have enumerations. which are not quite C enumerations. They're more like SML and OCaml data types, and this is the algebraic data types of those, where each variant can have data on it. I'll actually show you that in a second. But when you have an enumeration, you can match on it. You can look at what's inside, and then the compiler will automatically check that each match statement is exhaustive, which means that you checked everything, and you have to explicitly do something for every variant. So this was the case where enums can also contain data on them. So in this case, I have many possible shapes. My circle can have a center and a radius, and my rectangle can have a bottom left and a top right. And if I have a draw function per se, I can kind of match these, and I can specialize based on the shape provided. So this is where we depart a little bit from C++ enums, like C and C++ enums, where these can have data, but they're all represented kind of the same way, where this is compiled down to just a union at compile time, where there's a tag saying which one it is, and then all the data is kind of all laid out parallel in memory. It doesn't actually take up tons and tons of memory. So I was talking a little bit about ampersand pointers, and you actually get some nice optimizations around them, where an ampersand pointer, you're guaranteed, is never null. The Rust compiler guarantees at compile time you can never ever have a null pointer reference, but you can have a nullable reference in this case with the canonical option type. So option in Rust has two variants called sum and none, where sum has some data and none has no data. So in this case, we know that at runtime we can represent this, even though it's a generic enumeration which generally has a little bit of extra tag overhead, because it's a pointer we can just null it out. And so the mutable pointers actually has some very interesting properties around it, where Rust will guarantee there is never more than one mutable pointer to your data at any one point in time. So this is a very, very interesting guarantee, which you can build a lot of interesting abstractions on. So if I know, like for example, it's it's a linchpin of safety per se, in the sense that if I know that I have a mutable pointer to my hash map, I can reallocate anything I want. I can kind of reallocate vectors, I can resize vectors, I can push anything on, I can modify my internal state, because I know that no one else is looking at it. I know that I'm the only one that ever likes to look at it. And the other important part here is that if I have a mutable pointer, I know that no one else on any other thread can be accessing my data at that time. So having a mutable reference is a very powerful guarantee in Rust, where you can do lots and lots of fun things. And behind a shared reference, you are a little more limited, and this is why any mutations are allowed behind a mutable pointer. And this means that, and because it cannot be shared across threads, you can't have data races. And there's lots of fun little guarantees. If you kind of look through the standard library, you'll see some interesting types that rely a lot on mutability at this level. So you have to have it mutable before you can talk to it, and that means you have the only reference to it at that point. And this also enables some interesting optimizations in LLVM. So if you take a bunch of mutable pointers into a function, by default we know they don't alias. And aliasing is kind of a very fancy term for overlapping in LLVM. And LLVM can enable a lot of interesting things like vectorization, or a couple of memcopy optimizations, if it knows that pointers do not alias coming into the function itself. So Rust has traits. If you're familiar with Haskell, I'm told these are very equivalent to type classes. What this is essentially is that a trait, it can be implemented by any type, and every type will have this one function called clone. So this is an example trait. This is actually in the standard library, where it says, this is how I go from a shared reference to an own reference. The capital S self there on the side is actually just the type implementing it. So this is a trait which says, this family of types can go from a shared reference to an own value. And an implementation of that would kind of look a little bit like this. So from that point from earlier where I have an x and a y value, my clone would just set my own x and y values, and I'd have a new version of myself at that point. So what you can, and then the most powerful thing you can do with traits is you can put them in bounds. So this is kind of how Rust gives you functionality in generics. Rust has generic functions in the manner that C++ does, where we do this thing called monomorphization, which essentially means that if I clone a vector of ints and I clone a vector of strings, I'm going to get two copies of this function. One of them is optimized for just integers, and the other one is optimized for just strings. So you get some really nice performance guarantees from that. And then inside of here, we know that we can actually clone this t value of what the vector is, because we have this clone bound. If we don't have that bound, then we can't actually do anything with the values inside. We can kind of look at them, we can pass them on, but we can't do anything because we only know that it's an opaque type t. So traits allow us to have some more interesting functionality inside of generic functions. So I've told you a lot about how Rust is a very safe language. It's preventing all these data races. It's preventing all these weird bugs called like site faults and use after freeze. But there is another side to Rust. There is a side to Rust where you can break the rules, and that is called unsafe code. So Rust is a language where it understands that you cannot, having all these restrictions that I was telling you about earlier, like own values with boxes and RCs and all these channels, it's not sufficient. You can't do everything you want to do with just that abstraction. Those are kind of the abstractions which we have given you. They're very, very common, but they're not everything. They're not everything that everyone will think of. And for that purpose, Rust has unsafe code, where what happens is when you have an unsafe block, you're telling the compiler, no, I got this. You don't have to worry about this. So it turns off a couple of compile time checks, and a couple of things are only allowed in unsafe code. So this is an example of just kind of a casting expression, and this star constant and star mutant, those are raw pointers. It's just kind of values at runtime, or values at compile time, we know nothing about them. And here, we're dereferencing the raw pointer and storing into it. That operation is only allowed in unsafe code. So certain operations are, I'll talk about a little more in a second, but here you can see that the local variable A is declared as 3. It's not mutable. But in this unsafe code, I actually reset it to 4, and then I print it. This is actually going to print 4. It's not going to print 3. If we run it, we can see it prints out 4. So unsafe code is where you have the opportunity to kind of break the rules, kind of get around the type checker, not necessarily the type checker, but get around the type system and kind of the ownership and borrowing system, where the goal in Rust is to kind of minimize the set of unsafe code in a program. We understand that there will be some unsafe code where the compiler just cannot understand that this is actually a safe operation. But as a programmer, what you're saying is, okay, compiler, if you look at this atomically, this is totally safe. If you look inside here, you can't act like, you will generate errors, and I don't want you to actually generate errors. So Rust code strives to minimize the amount of unsafe code as much as possible. And what that eventually means is that if you want to audit a code base, for example, all you have to do is generally look at the unsafe blocks, and you can kind of go from there. It's a very much smaller proportion of the code base to audit than the entire million lines that like WebKit is. So some other unsafe operations that the compiler allows is I can call an unsafe function. So that's a very powerful operation because we have this very fun function called transmute, where what it does is it takes a type T and gives you a type U. So as you can see, this totally breaks the type system. This is just taking anything and giving you anything back, as long as they have the same size at runtime. So this is a very interesting operation where I can erase mutability per se. I can take this shared pointer, which I can't mutate. I can also turn it into a mutable pointer. And it's a very unsafe operation. Now, this is very necessary to build these abstractions on, but this is kind of one of the building blocks that the standard library allows you to have. And then one of the last things that you can do with unsafe code is you can call external functions. So FFI stands for Foreign Function Interface, which is kind of a fancy word for saying Rust can talk to C. And what Rust does is it gives you, the FFI interface in Rust is actually very, very first class, and it's very easy to talk to C from Rust. So in this case, there's the write syscall in C, which is kind of write some data to standard out. So I'm actually writing the hello world program from the first slides in essentially C at this point, but I have to use this unsafe block to actually call this function because I have no idea what's going to happen to that function. It may not even respect the signature I just wrote down. It may mutate random things in the stack. But we can see if I run this, it'll print hello world as it's just called the write syscall in C. And so another thing about Rust FFI is that it's actually really, really fast. If you take a look at the disassembly of the main function in assembly code, you can see that this is actually literally just a call instruction with the write function. So there is zero overhead whenever you do Rust FFI, is what this is amounting to, is that you might have to translate some types, but beyond that, there is no overhead in actually calling C functions. So another question I get a lot is, should I be using Rust right now? And my answer is yes. I think everyone should be using Rust. And some reasons for that I would give behind that is that Rust is very, very good at large, maintainable, and scalable systems. Rust is a code, generally when you have a lot of static analysis in your compilers, and whenever you want to refactor, it's a lot easier to do that than in a language like Ruby. Because if you have a language like Ruby, then I've had horror stories where you change a method, and then years later, you're still finding places where you forgot to go and update the callers of that method. But in Rust, with a compiler and a very powerful type system, you can actually guarantee that your changes are actually totally safe for the entire system. Not only do they compile, like in C++, but they won't ever call segfaults after that. So Rust is also very good about embedding into other languages. So one of the primary users of Rust in production right now is a company called Tilde. They have a product called Skylight, which is a Rails monitoring app, and they have their agent, which is collecting all the data and kind of crunching all the data. It's all entirely written in Rust. So this is a Rust component which is plugging into arbitrary Ruby processes around the world, everyone's random Rails process. And Rust is very, very good at that. The interface of crossing into Rust is very, very cheap. It's very easy to do, and it's very easy to embed Rust into other places. I've seen extensions for Python as well. Someone was actually recently working on, you would write some Rust code, and you would write some Python bindings, and all the unsafe code would be generated for you, and everything would be totally safe at compile time. You wouldn't have to worry about it. And then Rust is also very, very good at writing fast and correct code. And when I say fast, I mean this is actually very, very fast. This is C++ level fast. It's kind of what everyone expects out of a very powerful optimizing compiler. But at the same time, Rust is very, very good at writing correct code. If I don't write unsafe, it's very, very difficult to get a segfault. And if you do, it's a bug in the compiler or a bug in the libraries. So as an example of this, Rust's package manager called Cargo is entirely written with 0 unsafe blocks. So this is a fairly large project, which I've been working on for a while now, and I've been able to write the entire thing with no unsafe code, and I've never had a segfault in it. So this is something that Rust is definitely very practical in its use cases. You don't have to resort to unsafe code very, 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 very frequently. So the other question is, after I tell you should be using Rust, you ask me, okay, should I be using it right now? And my answer is a little more nuanced. I'm not actually sure you should be using it right now. So Rust is not yet at 1.0. The library and the languages will continue changing. We can continue adding features, continue removing features, continue doing some interesting things with libraries as we continue to experience. Now this is changing. We are very, very close to 1.0 at this point. We've been saying that for like 6 years now, but we're actually very, very close to 1.0 at this time. We plan on having a 1.0 beta or 1.0 alpha release out in early January, and from there we will have at most 1, 2, maybe 3 beta cycles, and then from there we will have a 1.0 release. So by this time next year, we will definitely have a 1.0 release, and I expect it much, 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 much sooner. So I will say, however, Rust is a lot of fun to work in. There's a great ecosystem going on now. We have our package manager just kind of came into existence. We have a hosting site online called crates.io, and you can kind of upload all your packages, see everyone else's packages, explore code from there. We have a really active community. It's a lot of fun to play around in, and it's great for actually writing some real world code if you would like to start dabbling and kind of maybe rewriting small components here and there in Rust and kind of see how it works out. So that's all I have. I have a couple links here, like all of our code is on GitHub. You can kind of just browse the whole repository. We have a website called rustling.org. It's got some links to documentation, to guides, which was recently rewritten and is very, very high quality. I highly recommend it if you'd like to dive a little more deeper into Rust and kind of just this high-level overview. We have a subreddit which is pretty active for lots of news around Rust, and the Pound Rust IRC channel on mozilla.org has hundreds and hundreds of people always willing to help. That's a lot of fun. So thank you for listening to me talk about Rust.